Now, today's topic is to define current density. We want to obtain Ohm's law in terms of current density. Okay, then this question can be asked obtain Ohm's law in vector form, or it can be asked obtain J is equal to sigma E. Here, J is a current density, okay, and J is current density, okay, and E is known to you is intensity of electric field and sigma is conductivity. So we want to derive this formula J is equal to sigma E. Okay. Now here first of all current density is nothing but current per unit area. Okay, current per unit area perpendicular to the current. Try to understand area, or we can say the plane that we are considering, or cross section of the conductor which we are considering is perpendicular to the current. Okay, so I am drawing it for understanding. Say for example, this is the conductor, and if you consider the cross section of the conductor this way, and direction of electric current is from left to right, then we can say that this plane which we have considered, this plane is perpendicular to area. Try to understand, I am talking about the plane of cross section that is perpendicular to the direction of current. So current per unit area, so area is perpendicular to current, which is defined as current density denoted by small j. So J is equal to I upon A. Here A is vector quantity because area is a vector quantity. Okay, if I take the area vector in the direction of electric current, okay, so here J is equal to I upon A. Current is a scalar quantity. Try to understand, it is charge per unit time. Electric charge upon time. Charge is scalar, time is scalar, so electric current is a scalar quantity. But here area is vector quantity, therefore this current density J becomes vector quantity. So A is a vector quantity, therefore this J, that is current density, is also a vector quantity. Now if you write in this way, I is equal to J, that is current density, multiplied by area, current density multiplied by area. Now try to understand, we are having current I, that is result of product of two vector quantity. Try to understand, current I is the result of the product of two vector quantities. Now which are these two vector quantities? J is current density, A area. Now both the vector quantities, if they are multiplied and they are giving you the result as a scalar quantity, then this product must be a scalar product, and therefore we can write I is equal to J A, that is area, sorry, capital A you can write, small a sometimes it is written in some of the textbook. Okay, J A cos theta. So try to understand this concept. The product of two vector quantity results in a scalar quantity. It means that it must be a dot product and it must be I is equal to Ja cos theta. Okay, that is why it is written as I is equal to Ja cos theta. Okay, the equation in the vector form can be written as J is equal to I upon A. So J is vector, I upon area vector. And as you know, the unit of current is ampere and unit of area is meter square. So unit of current density is ampere per meter square. Okay. Now try to understand it in a different way. Say for example, this is the conductor in which the current I is flowing. This is the direction of flow of electric current. Now if the cross section is taken slanted, if area is taken to be a slanted, then as you know that area vector is always perpendicular to the plane, so this will be the area vector. This will be the area vector. And this is the direction of electric current, that is I. The angle between them is say theta. Then if you take the component of area in the direction of electric current, then that component will be A cos theta. A cos theta. So according to our definition, if you want to write, say J is equal to current upon area, but that area must be perpendicular, or we can say area, that is plane must be perpendicular. Try to understand this part. The plane must be perpendicular to the current. This plane is not perpendicular to the current. If you take the component A cos theta, then that A cos theta will be in this direction. Okay, and this A cos theta component of the area will become, A cos theta component of area will become perpendicular to the direction of electric current. So A is in this direction, but A cos theta will become this way. Okay, and this A cos theta will be the plane which is perpendicular to electric current. So J is equal to I upon A cos theta. So I is equal to, you can write Ja cos theta. This is the significance, or we can say understanding of this definition of current density. So generally both the way it can be understood, that you have to take the component of area vector in the direction of electric current. If that area vector, say for example, is taken in the direction of current, then area is in this direction, current is in this direction, then the component will be A cos 0. So it can be written directly as J is equal to I upon A cos 0. Cos 0 is 1, so J is equal to I upon A. But if that area is like this, then you have to consider the component, that is area vector would be like this, which is making an angle of theta with current I. Then you have to consider the component of A, that is A cos theta. Okay, and we write it in a formula that I is equal to Ja cos theta. Okay, this is significance or understanding or conceptual understanding of this definition. Okay, so we have now different formulae. Try to understand first formula, first equation. Only you just have to list them out. First formula is J is equal to I upon A. Then we know that V is equal to IR, that is Ohm's law. Okay. Now from equation 1 you can write I is equal to JA. Okay. J is equal to I upon A. So you can write I is equal to J into A. Now if potential difference V is applied across the two ends of the conductor whose length is L, say for example you have one conductor, say this is a conductor which I have tried to explain 2-3 times, and if you apply the voltage here, okay, then potential difference across the two ends of this conductor is V, and the length of this conductor is L. Then we have the equation that we have studied. Okay, V is equal to E into D. Here D is replaced by L. So we can write V is equal to L. That will be your fourth equation. So list out all these equations. J is equal to I upon A. So I is equal to JA. V is equal to IR. And V is equal to EL. Okay. Now, as we have the another equation that also we have studied last time, R is equal to rho L upon A. Okay, rho L upon A, where rho is a resistivity, L is the length of conductor, and capital A is the area of cross section. So these are the equations that we have to list out. J is equal to I upon A, or I is equal to JA. The other one is Ohm's law, V is equal to IR. This we have studied, V is equal to E into L, and R is equal to rho L upon A. Now using these equations, okay, substituting equation 4 and 5. Equation number 4 we have to consider, okay, and this fifth equation we have to consider, and we put them in equation number 2. So instead of V we write EL. Okay, so here we are writing EL, and instead of R we are writing rho L upon A. So we will have, say for example, if you simplify it, okay, then instead of this V, okay, instead of the voltage V, we have E into L, and instead of this R we are writing rho L upon A. So it becomes EL is equal to I rho L upon A. Now I upon A is nothing but J, so it has been replaced by J. So EL is equal to J rho L. Now from both the side L will be cancelled out, so we can write E is equal to J into rho. And if you want to write this in vector form, because E is a vector quantity, J is a vector quantity, so it can be written as E is equal to J rho. Okay. Now conductivity and resistivity, they are inverse of each other, or we can say we can define the conductivity as inverse of resistivity. Okay, so sigma is equal to 1 upon rho. So instead of rho you can write sigma, so it can be written as E is equal to J into 1 upon sigma. So J can be made as a subject of formula. So J is equal to sigma E is the required equation which we have to derive. Okay.